All right, well, welcome back for our next discussion and continuing on in 8.2 in integration by parts. We're going to look at some more examples of using integration by parts and some shortcuts along the way, as well as taking the technique of integration by parts and applying it to evaluate certain functions that we haven't been able to take the antiderivative of before. And so if we start out, we're going to start with x cubed e to the 2x dx. And if we want to evaluate this indefinite integral, at first glance, you may think we need to do integration by parts 3 times over. And yes, you are absolutely correct. You need to. However, I don't need that much board space to get this answer, because when I do integration by parts 3 times over, I'm going to make the same choice every time for u and my dv term. My polynomial is going to be x cubed. Now I'll choose that for u every single time because I'm going to want to decrease the power of x to eventually when it's a constant. And I do that because, of course, regardless of where e to the 2x is, my new integral will always contain a form of e to the 2x in it. And so my only hope to eventually answer this is to get to a point where I have e to the 2x times a constant. And if I can do that, then I can finally answer the definite integral, or the indefinite integral. So instead of doing integration by parts out 3 times over, I'm going to kind of synthetically do it, right? You remember from algebra synthetic division, where it's long division of polynomials in certain cases, and you can kind of shortcut it using like coefficients. In the same way, I'm going to shortcut integration by parts. And the reason is because I'm making the same choice of u and v every single time. And that is that my u will be the polynomial and my dv term will be the exponential. So my first choice of u and dv is x squared and e to the 2x. Now I take the derivative of x squared and the antiderivative of e to the 2x. Now the antiderivative of an exponential is the same exponential. The chain rule, though, is going to give me a 1/2 in front. That's an exercise in u substitution. So verify that I promise the antiderivative of e to the 2x will give me 1/2 e to the 2x. Every time I take the antiderivative of e to the 2x, I'll get an additional 1/2 in front, multiplied in. Now we'll be consistent. And so the next time I do it, we have this new derivative and antiderivative. This product is my new integral, the second line. I can't answer this product either, so we continue on. I do integration by parts again. The derivative of 2x is 2. The antiderivative of this was now 1/4 e to the 2x. The 1/4 comes from another 1/2 we get. 1/2 times 1/2 is a 4th. I get to this place, and technically I could answer it, but I'm lazy because I can make it a little easier on myself. If I continue one more time, the derivative of 2 is 0. The antiderivative here is 1/8 e to the 2x. So 1/8 again because we multiply by 1/2. Why do I do that? Because now this last term, this product is the final integral that I'm going to have to calculate. However, when I multiply this by 0, we get the antiderivative of 0. 0 times that is 0. And the antiderivative of 0, well, it's not an x or anything like that. It's a constant. That's going to be my plus c at the end of my integral. So where's the plus c come in? Comes from the last line. And so I continue on until I hit 0 here, because then this product is the last integral that I need to take. However, 0 times anything is 0, and the antiderivative of 0 is going to be your plus c. Now, the reason I can stop here is because every time you do integration by parts, you get part of your answer for free. We got to a place where we get a definite integral. It's just going to be a constant. And along the way, every time I do integration by parts, I get part of my answer. What is each part? It's u and v. Now, we have to be careful because it's u and dv. So my first u and v is this guy here. Right? It's the u that you chose and the antiderivative of e to the 2x. That's my first u and v. My next u and v will be this one. And finally, my u and v, my last one, will be this one. Every time I do it, I did it 3 times over. So my u and my v from my first time I did it, the u and the v from the second time, and the u and the v from the third time. And then finally, the last integral you get ends up just being a plus c. And so I have the product, or all the terms in my answer. The first product is these two multiplied. So 1/2 x squared e to the 2x. The second term is 2x times 1/4. Now 2 and 1/4 simplify to 1/2 again. X e to the 2x. And then 2 times 1/8 e to the 2x. Now the 2 and 1/8 simplify to 1/4. And then finally, this last integral just gave me my plus c. Now, the only thing you notice is that I didn't put any signs between these terms. Now, we have to be careful, and that's because of how integration by parts works. Remember that integration by parts is uv minus a new integral. So every time you do integration by parts, the new integral you get has a minus sign in front of it. So it's a negative of that indefinite integral. And so the first time you do it, you get uv. That's just there. Then you get minus a new integral. So the next time you pull out a uv, it has a minus in front of it. So it's negative, this product. So this one was just plus, this one is minus. If I do it again, now it's minus that integral, and I do it again, there's another minus sign when I do it again, which is minus minus, which is now back to plus. And so it alternates sign. And this is the correct antiderivative. You know, we don't need a minus c because c could be negative or positive, so that's just always going to be plus, but here's my answer. Now, don't worry, we're going to do it a little more time. We're going to do it here, and you notice this one is familiar because we did it in the last video. And I'm going to shortcut it and get the same answer we got in the last video, but using this shortcut technique. And so I'm going to use u and dv, make a choice. And the reason I can use this shortcut is because eventually this chart will end. It will stop at a certain point where I can get an answer. So I'll keep my polynomial as my u and continue to take its derivative until I hit 0. That means I will now have sine of 2x here and continue to take antiderivatives until I've completed this chart. So antiderivative of sine is negative cosine. Antiderivative negative cosine is negative sine, but again, every time, just like the last one, we're going to get a 1/2 out front. And antiderivative of negative sine is now cosine. Another 1/2 out front is going to give me 1/8. So now positive 1/8 cosine of 2x. And the reason I stop here is because remember now this last product is your new integral, right? That's going to be the last integral now we need to evaluate. But I stop here because it's 0 times, well, who cares? Because this is now the integral of 0, and the antiderivative of 0 is a constant. So that's going to be your plus c at the end. So it's going to give you this. Everything else you got for free by filling out this chart. You get your first u and v. That's going to be negative 1/2 x squared cosine of 2x. That product. Minus, because it's going to alternate sign, this product. So plus that product, minus, and the reason it's negative, even though it's plus here, it's negative because this term was negative. So it's plus this product, which is negative, minus this product. Now be careful because it's minus this product, but this product has a negative already. And so now it's actually back to positive. So just be careful with signs. So I'll just write it and then we'll simplify. So minus, and then 2x times negative 1/4. Now 2 and 1/4 simplify to 1/2. So negative 1/2 x sine of 2x. And then finally, back to plus that product. Now 2 and 1/8 simplify to 1/4. So we have 1/4 cosine of 2x. And then my plus c. Now the only thing to fix would be the negative here, which makes plus. And here's my answer. Now that was a lot faster than what we did in the last discussion. We didn't bypass doing integration by parts. We did it. We just kind of did it synthetically. Instead of writing it all out, we did it via a chart. Now this may be helpful, and this is only helpful in certain situations. You notice in both these cases, the reason it worked is because my u was a polynomial that eventually went to 0. That will work, and that will be the scenario in which we can use this. So if I have like x to the 5th times an exponential, or x cubed times a trig function, I can use this type of shortcut, as long as you can take the antiderivative of the other one. Like, we can take antiderivatives of sine, we can take antiderivatives of exponential, so we could fill out this chart. This would not have worked with that ln of x example in the last discussion. The reason being is because you wouldn't be able to take the antiderivative of ln. And so this gives us a kind of nice way to kind of shortcut integration by parts in certain scenarios. And what we want to do right now to finish up this discussion is to apply integration by parts to answer antiderivatives of functions that we haven't been able to address yet. So, and we'll also look at a definite integral. So antiderivative of just ln of x. Now, of course, you realize, hey, integration by parts, you need a product. Now, be careful. In math, there's always a product, even if it's not explicitly written. You can always think of a function as a function times 1, right? And so there's an imaginary product here, so we can use integration by parts. Choose a u and a dv. Now, of course, I should not choose my dv to be ln. Why? Because, of course, that would imply you knew the antiderivative of ln, which you don't, right? Otherwise, we wouldn't be doing this. So we will choose our u to be ln and our dv to be this 1 dx. That way, I do know the derivative of ln, and I do know the antiderivative of 1 is x. I get part of my answer for free, u times v, x ln of x, minus a new integral. The new integral is the product of these two things. Now here, x times 1 over x, the x is actually reduced and just give me 1 dx. X times 1 over x, the x is canceled. And we can actually now evaluate this explicitly. We just need integration by parts once. Antiderivative of 1 is x, and plus c, and we're on our way. So now we actually know the antiderivative of ln. It's not very nice, but it is done now. We do know it. It's x ln of x minus x. That is the antiderivative of natural log. And we need integration by parts to do it. The same is going to go for the next example, using arctangent as an example. We don't know the antiderivative of arctangent, but you do know its derivative. And so I'm going to use the same exact idea as we do with ln. Choose a u and a dv. I'm going to have an imaginary 1 multiplied, so that's going to be my 1 dx, and u is going to be arctan. So although we don't know the antiderivative, we do know the derivative of arctan. Now, you may not remember it off the top of your head, but if you look back, we discussed in Calc 1, 1 over 1 plus x squared dx, and the antiderivative of 1 is x. Now, this is a definite integral, so just remember that when we find the antiderivative, there's not going to be a plus c at the end, but we're going to take the antiderivative and plug in 0 and 1, evaluate it. So we just need to be mindful of that. So we get part of our answer for free, so x times arctangent of x. And this will be evaluated from 0 to 1. That's part of my answer, part of my antiderivative, evaluated at these endpoints. But of course, we still also have a new definite integral, and that would be this product. So we have x over 1 plus x squared. However, in the second term, although it looks complicated, this is now a very simple u substitution problem. If you look at the denominator, 1 plus x squared, the derivative of 1 plus x squared is 2x. So let's put a 2x there by kind of adjusting that constant. That way, if I do a u substitution now, let's do a different color. U is 1 plus x squared. It's not integration by parts, but just u sub now, 2x dx. We can transform this second integral into 1/2 1 over u to u. And then we would change our bounds, right? And of course, in this case, my old x bound was 0, my new u bound is 1. My old x bound was 1, my new u bound is 2. So what do we end up getting? We end up getting x arctangent of x. That needs to be evaluated from 0 to 1. We get a new integral that I did u substitution on. Those bounds are now 1 to 2, 1 over u du. And let's go ahead and evaluate it. So x arctan of x from 0 to 1 minus 1/2. Antiderivative of 1 over u is ln of the absolute value of u, evaluated from 1 to 2. So now we just need to plug in some bounds. So plugging in 1 here, we get 1 times arctangent of 1. So we get arctangent of 1 minus 0 times arctangent of 0. So 0 times this is going to be 0, so that term's gone. Minus 1/2 ln of 2. And then, of course, we would have to minus 1/2 again. But when we plug in 1, ln of 1 is 0. So actually, we don't care about the second term. And so that's the only term that's going to be left. And then if you're really good with inverse trig, you know arctangent of 1 is the angle in which tangent is 1, which is pi over 4. 45 degrees. So arctangent of 1 is pi over 4, and then we have minus 1/2 ln of 2. So this number is the evaluation of arctangent of x from 0 to 1. So again, this is just a practice in, of course, integration by parts, but also using definite integrals. I mean, the only difference at the end of the day is taking that antiderivative and plugging in your bounds. If this part throws you the fact that I've changed bounds, don't forget you could always go back and use your original bounds. So I could go here now, and antiderivative of 1 over u is ln of u. Remember, u is 1 plus x squared. And then, of course, we could take this whole antiderivative and evaluate it from 0 to 1 now, instead of 1 to 2. Okay. And so if I plug in 1, we get 1 arctangent of 1 minus 1/2 ln of 2. Minus, if we plug in 0, we get 0 times this, which is 0. Here we get minus 1/2 ln of 1, but ln of 1 is 0. And so that second term when you plug in 0 is gone. And again, you end up with this. So either way you want to do it. I just changed the bounds using u sub, so I wouldn't have to worry about back substituting. But if you don't like that, you just find the general antiderivative in terms of x, which was here, and then use your original bound 0 and 1, and you'll get the same answer. So either way, we can find antiderivatives of other functions using integration by parts. Is kind of a hack, right? It's not like I'm necessarily given a direct product initially. It can be thought of as times 1. But we can use this technique to our advantage and then also apply it to definite integrals. The only difference is taking that antiderivative and plugging in some bounds. So I hope that was helpful, gave you a little more examples and using integration by parts, get you comfortable a little bit more. And when we come back, we'll move forward and talk about our next technique of integration. So I'll be talking to you guys soon.